All right, in this video we're going to introduce eigenvalues and eigenvectors using some geometrical considerations. So eigenvectors using geometrical considerations. So in fact, what we're going to do is we are going to recall that matrices can be considered as transformations in the xy plane. Okay, so we are going to consider the effect of matrices. Let's call them transformation matrices on two-dimensional vectors. So here we're just going to confine ourselves to two-dimensional vectors. So consider the effect of transformation matrices on 2D vectors on two-dimensional vectors. In particular, so we're just going to use a particular example. We're going to consider the following matrix. So consider the effect of the matrix A given by 1, 4, 1, minus 2. So consider the effect of this matrix on, let's look at two vectors. Let's start with 0, 1, and then we're also going to do vector W. Suppose vector W is negative 2, 1. Right, so I want to see what the effect of this matrix is as a transformation to these vectors. So we're going to go to our xy grid so that we can see what these effects are. So on this grid here, we can see that the vector u, we already have it there. So that is our vector u, and this is our vector w. So remember, u is 0, 1, w is minus 2, 1. Okay, so let's look at what happens when we when we apply the matrix A on U. So let's work out AU here. So I've got 1, 4, 1 minus 2, probably let's change our color. So 0, 1. So when we do this, it's going to be 4, and this is minus 2. So what this thing is telling us is that the image of U under the action of A is 4 minus 2. So that means it it's this vector here. So that is a u. So a u there. So just for comparison, so the first thing we notice is that the magnitude of A has been altered, and also its angle has been altered, because A is along the 90-degree line, but AU is in the fourth quadrant. Right, next let's see the effect of A on W. So we have got 1, 4, 1 minus 2. W is minus 2, 1. So this is going to be 4 minus 2, which is 2, and then the other one is going to be minus 2, minus 2. So it's going to be minus 4. Okay, so this time this vector, the image of W is going to be 2 minus 4. So that vector is going to be right about there. Okay, so it's just so that vector, maybe let's put it in this color, right about there. So that is a W. So again, its angle is altered, and notice that the change in angle for W is bigger. Well, let's just say it's different from the change in angle of U, because it depends whether you're looking at things in the counterclockwise or clockwise direction. Okay, so we see that when A acts on U and when A acts on W, the image in both cases has got a different magnitude and a different direction. Okay, so let's go back to our page. So the thing we have seen is that in general, the effect of A on vectors in the two-dimensional space. So let's say on any vector, let's say any non-zero vector. So effect of A on any non-zero vector, non-zero vector is a change in both the magnitude and direction. Okay, so for instance, U was along the vertical axis, and then its image was in that direction. Now, however, let's just observe what's going to happen. What happens if we transform the vector V, let's call it V, imagine that V is 4, 1. Let's see what happens when you transform this one by that same metric. So let's go back to our XY grid again. So this time there is our vector V. So it's a green vector here, and so let's see what's going to be the image of this vector under the matrix A. So a V, so there's our vector V. So that's going to be 1, 4, 1 minus 2. V is 4, 1. So 1 times 4 plus 4 times 1 is 8. And then 1 times 4 and then minus 2 is 4. So this is 8, 4. So 8, 4 is right there. So the image of V is actually going to have the same direction as V. Okay. If we go back to this one, we can actually write this vector because there is a common factor. Just one moment. That is 8, 2, not 8, 4. So here this is supposed to be 2. So we can write this vector as 2 into 4, 1, which is the same as 2 times V. So AV here is 2 times V, which is confirming that it is actually in the same direction as V. So notice we just concluded this side that generally when A acts upon any vector, the effect is a change in both magnitude and direction. But when we act A on this vector V here, only the magnitude is altered. The direction remains the same. Okay, so maybe let's just note that. So we see that A times V is equal to 2V, i.e. the direction of V remains invariant, under the action of A, Okay. So that means this vector V has got a special relationship with the matrix A. Okay, so yes, indeed, V is a special vector to the matrix A, and this special vector is called an eigenvector. Okay, so it's an example of what we call an eigenvector. Now, if we just go back and check here, so the direction remains the same, but the magnitude of AV is twice the magnitude of V. So that is V there, and then AV is 2 times the magnitude of V. So this matrix which whose direction remains invariant under A is called an eigenvector. So the effect of A on this vector is just to scale it. Either it becomes longer or shorter. And the scale factor in this case is 2. And that scale factor is called an eigenvalue. Okay. So the eigenvalue associated with this eigenvector for this matrix A, so the eigenvalue is 2. So that is the relationship between the eigenvector of a matrix A and its eigenvalue. So a vector or an eigenvector is that vector that remains whose direction remains invariant under the action of the matrix. So it is only multiplied by a scale factor. That scale factor is called the eigenvalue. Right, so let's just put that down in words. So what we're saying here is that so we see that direction of that. Okay, so the vector V is called an eigenvector of matrix A, and the scale factor, so when we act A on V, we end up with 2V. So the scale factor is 2. So this one here is called the associated eigenvector, is the associated eigenvalue, eigenvalue, right? In fact, if you take any other vector in the direction of V, you will find that the effect is exactly the same. So the effect of A on any other vector along the direction of V is going to be the same. It doesn't matter its magnitude. So let's do an example. For instance, here, suppose we've got a vector alpha. Let's take it in the opposite direction of V. So this vector alpha is has got this relationship with V. So if V is going this way, so remember V is 4, 1, then that vector alpha is going this way. Okay, but its magnitude is half the magnitude of this one, so that's -2 minus half. So let's see what happens when we act A onto alpha. So I've got 1, 4, 1 minus 2 minus half. Okay, so this is going to be -2 minus 2, which is -4. This one is going to be minus 2 plus 1, which is going to be negative 1. So as you can see, this is going to be 2 times times that. So it's 2 times alpha. So in fact, if you take any other vector in the direction of v, it is also going to be scaled by 2, which is the eigenvector. Now, just in terms of the terminology, so notice that the term eigen is borrowed from the German language, is borrowed from the German language, or just German, where it stands for any of the following synonyms. In that case, own, so eigenvector is like its own vector. Spatial, okay, so we have already mentioned that these vectors are spatial because they're the only ones that remain invariant in direction. The other synonym is characteristic. Okay, characteristic. So these are all the forms in which this German term eigen gets used in that language. Now, so in general, a 2 by 2 matrix is going to have a maximum of 2 eigenvectors. So a 2 by 2 matrix has a maximum of 2 eigenvectors. On the other hand, 3 by 3 matrices have a maximum of 3 eigenvectors, and of course each eigenvector has got an associated eigenvalue. So given an n by n matrix, A, so the non-zero n by 1 vector v is called its eigenvector, provided A times V is equal to lambda times V, where lambda is a scalar, a non-zero scalar. Okay, where lambda is a scalar. Well, which is the corresponding eigenvalue. So lambda and V go hand in hand. Lambda is the eigenvalue, V is the eigenvector. Now we're going to have to manipulate the the equation 1 so that we can get a formula for finding the eigenvalues. Okay, so we express 1 as follows. So the thing is here, the matrix on the, or rather the situation on the left hand side, this one is n by n, whereas this one is n by 1. So we're going to have to manipulate this side so that it is also n by n. So this is what we're going to do. We're going to say AV is lambda times V. Then we're going to use the identity matrix here. So using that, we're going to write the right hand side as lambda times the identity matrix times V. We know that I times V still gives V, but the difference is that these two are now of the same dimension. Okay, then we're going to bring this term to the same side as this one, and then we can work with this because so the matrix arithmetic agrees because they're of the same dimension. Now V is now common, so we can factor out V. So we're going to get A minus lambda I times V. So there's going to be a system of equations. Now, by the theory of linear algebra, this system is going to have a non-trivial solution only if the following is satisfied. So this system has a non-trivial solution. Non-trivial means a solution where, or let me just say, it's a trivial solution if you have all the variables being equal to 0. So that let's call it 2. The system 2 has a non-trivial solution only if the determinant of this n by n matrix is 0. Okay, so determinant of A minus lambda I is equal to 0. This, let's call it equation number 3. 3 is going to be an nth degree polynomial. So this nth degree polynomial, so the unknown here is lambda, of course. So it's going to be an nth degree polynomial in lambda. Okay, this is called the characteristic polynomial. Characteristic polynomial of matrix A. Okay, so and when we solve that one, we are going to find the eigenvalues, and then when we find the eigenvalues, we can work back and find the eigenvectors. Okay, but we are going to go through those calculations in the part 2 of this video. Otherwise, at this point, thank you for watching. Do kindly subscribe so that you can get notified whenever we post new material. So in fact, the standard notation for that polynomial is this one here. So PA of lambda is the determinant of A minus I minus lambda times I. So that is your characteristic polynomial. All right, thank you. Of course, if you do have comments, would be happy to hear them in the comment section. If you want us to treat certain topics, do say so, and we will kindly oblige. All right.